Okay, welcome. So that's the wrong. Why have I got that screen up? What? Come back to that in a minute. Can we start off with the definition of rate of reaction, please? Rate of reaction. Where are we? 15. Is that right? What's going on here? You are late. Late on camera now as well. Still missing. That's not the rate. Oh, I see it is the rate equation. All right. What have you got, Jana? That's not going to cut it, I'm afraid. If you wait for an experiment to finish, we'll come to this in a moment, but reactions tend to peter out. Like when you stick the reactants together in a beaker, you get lots of excitement and action and gas produced and whatever it is. But towards the end of a reaction, it gets slower and slower and slower and slower and slower. It's really hard to spot that point where the reaction's kind of continuing and then it stops, because it just peters out and gets smaller and smaller and smaller. It's very hard to find that. So it's a very poor measure of rate. That's much better, because we can measure an amount of product and we can measure time. Those are very easily measurable, and that gives us a much more precise measurement of rate. Okay, does it have to be product? Or reactants. So reactants used up or products formed. So we have to measure some sort of amount, and we have to measure time. So amount of reactants that are used up or the amount of products that are formed over time. We've got to get time in there somewhere. The units of rate. Sorry, I'll put that back. Oh, what am I doing? That's what I'm doing. The units of rate. What could the units of rate be? Hang on, let people think. Think about what Jano just said. Say we're measuring the amount of product formed over time. What would the units of that be? Kieran.
I was thinking grams seconds minus one.
Okay, so grams per second or grams second minus one. So we've got to have a unit of amount, and we've got to have per time. Okay, there's lots of ways of measuring amount. There's moles and there's grams and there's concentration. So we're gonna standardize it so that pretty much every experiment you see is going to have the same units of rate. So we're going to measure it in change in concentration of reactant or product. Over time. Squeeze that in there. And we're going to have the units of rate be mole per dm cubed per second. So change in concentration over time, mole per dm cubed per second. Okay, so that's just to standardize things a little bit so that you're not always second guessing the units of rate. I think it's a fairly standard GCSE question. Maybe you're given a graph and you're asked what are the units, and it can change for different experiments. So we're just going to make it a bit, not simpler, but a bit more predictable. Okay. So the next question on the board, how does an increase in concentration affect reaction rate? Explain your answer. That's a very standard question. We've already covered this kind of thing. It was on the exam, wasn't it? How does an increase in concentration affect rate? Somebody just do that off the top of their heads? I'm looking at James, go for it.
There is more particles in a given volume.
More particles in the same volume, yeah.
Which increases the rate, which means more collisions.
More collisions,
More frequent collisions.
more frequent collisions, or increased collision frequency. Great. Okay, so that's the collision theory, isn't it? Collision theory states that. Anyone want to come in there? Collision theory states that. Come on, Matthew, you do this one.
It has to be a sufficient amount of energy for successful collisions to occur.
Okay, break it down into two bits. Collision theory states that. What are we talking about? What kinds of things are reacting here?
Molecules.
Particles, because it's not always going to be molecules. So particles is a safe word.
Particles have got to collide with sufficient energy.
That's it. That's it. That's the whole thing. Particles have to collide. That's the first bit. With sufficient energy. That's the second bit. Great. So if we increase concentration, we're not changing energy. We're just sticking more particles in the same volume. So that's going to increase the collision frequency. Remember that. It's rate of collision. It's not just more collisions. Right. If I double concentration of a reactant, how would that affect rate? What do you think, Kobe?
I'd say an increase.
Yeah. Notice the focus on the word double. Okay. So one of the things that we're going to move to here is we're moving from a qualitative answer. Qualitative just says this increases, that increases, towards a quantitative answer. If we double concentration, we would expect rate to double as well. Okay, now let's, that's just those answers there. So, yeah, that's already on the board there, isn't it? Changing concentration of reactant or product over time. Units of rate are going to be mole per dm cubed per second, or changing concentration per second. Increasing concentration increases rate because there are more particles per unit volume, which increases collision frequency. Notice the bolded words, those are our key words. If I double concentration of reactant, I would expect it to double rate. Okay, we're all good. Right, let's go back to the practical we all did then. Good old disappearing cross experiment. Don't forget to take it off freeze. In the disappearing cross experiment, you will remember, you have a flask, and into that flask we put some hydrochloric acid and some sodium thiosulfate, swirl it around and stick it on a cross. And the reaction produces that solid sulfur precipitate that makes it go cloudy, opaque, and then the cross disappears. And we measure the time taken for the cross to disappear, which gives us a measure of rate. Notice it doesn't give us a measure of changing concentration because we're not actually measuring the amount of sulfur appearing or the amount of thiosulfate being used up. but it gives us a measure of rate. Okay, and there's a reaction there. So my question is, sorry, I can't remember. Oh yes, I've got a nice pretty picture. My question is, if we did this experiment several times, and each time we change the concentration, so we do the experiment with a concentration of, I don't know, whatever they are, 0.1, 0.2, 0.3, 0.4, whatever, changing the concentration of the thiosulfate and measuring rate somehow. Let's not worry about how we measure rate. We measure the rate of the reaction. And I plot a graph of that data. What would that graph look like? I would like you just to draw a quick sketch in your books now. So we've got concentration along the bottom here of sodium thiosulfate and rate up there. What would that graph look like? Just want to see a quick sketch in your books. Anthony, what have you got there?
Straight line.
Does it go through the origin?
Yes.
Yes. Yes, it does. This is exactly what you should have. That's what we would expect. Other options are available. I'll come to that in a moment, but we would expect that. In fact, we do get that. If you change concentration, you get a straight line graph. What do we call a straight line graph that goes through the origin? You remember that, Sujan? Directly proportional. Okay. All right. Directly proportional. Okay. Let's put some symbols on it. What's our quick way of showing the concentration of sodium thiosulfate? How do we write that in a sort of an economical way? We put square brackets around. So I could write concentration of sodium thiosulfate, Na2S2O3 of sodium thiosulfate. Okay, underneath or somewhere near your graph, next to your graph, could you write a mathematical expression for that graph, please? Could you write a mathematical expression for that graph in terms of rate and the concentration of sodium thiosulfate? Okay, so we've got rate is proportional to the concentration of thiosulfate. If I wanted to write rate equals something, how would that change that equation? Go on, Eddie.
You put a K in front of it.
We put a K. What does the K stand for, Eddie?
Constant.
All right, so this graph, the directly proportional graph, you'll often see y equals mx is given as the general equation for all straight line graphs that go through the origin. If it doesn't go through the origin, of course, it's y equals mx plus c. But this one does go through the origin. So m here stands as our constant. Okay, great. Okay, yeah, that is it. All right, which gives us that. So we're going to call this, sounds a little bit over the top, we're going to call it the rate equation. And this is kind of going to be the main focus of our work this morning, the rate equation. Hang that up. Okay, so remember that notation, we use the square brackets around Na2S2O3 to mean the concentration of thiosulfate, and K we're going to call the rate constant. So rate is some constant times the concentration of a reactant is what we've got there. So K is called the rate constant. can we please make sure, does it come up here? No. Okay, be on the next slide. Can we please make sure that our little k, the rate constant, looks different from what other constant do we know? No, there's lots of other constants, but what other important chemical constants have you met?
Avogadro's constant.
That as well. One that begins with K. KC. Thank you. Yeah, we've met another K, which is the, what's KC? Come on, Addy.
The equilibrium constant.
Okay. All right. So we've got two constants which are both K's. So can we please make sure they look different? No sort of general kind of halfway K's that could be one, could be the other. Oh, that's how I do my small K's. No. Make your small K small and your big K's big. Okay. Which is why I tend to do the sort of the curly loop K. You know, the way primary school teachers do it. Just to make sure that it's really clearly small. Okay. Right. For reasons that will become clear, we say that rate is first order with respect to sodium thiosulfate concentration. Now that might sound like a bit of a mouthful. But first order. It's not a reference to Star Wars. It's a reference to that straight line graph. It's another way of saying that as concentration increases, rate increases in a uniform way. If we double concentration, we double rate. If we quadruple concentration, we quadruple rate. They'll always go up by the same amount, the same ratio. Okay. If you want to know where the first comes from, where's the one in that equation? Well, we could say that there's a one. It's to the power of one. The concentration is to the power of one. Now, of course, everything to the power of one is just itself. So you might think that's a bit pointless, but stay with me. There's a method in my madness. So we'll say that was first order. There are going to be other orders. All right. There's me. There's my little thing on spot the difference between K and K. Okay. Right. Let's do a bit of kind of clever experimenting now. We're going to do the same experiment, disappearing cross, but we're going to change the concentration of HCl this time. So we'll keep concentration of thiosulfate constant, just change the concentration of HCl. But we're going to do it in kind of an interesting way. So you might remember for my thiosulfate, I had sort of 0.1, 0.2, 0.3 going up. But what if we used much more HCl than we need? Let's say I have a concentration of 1, that's already a large excess. And then we went up 2, 3, 4. So we've started our first experiment with a huge excess, and then we've added even more HCl after that. And then we plot a graph just of those 4 experiments of concentration against rate. What would that look like? Okay, I'll come back to that. Could you, again, draw a little sketch in your books, please? If we add more HCl, that that probably won't have much effect on the rate. We've already got plenty of HCl. Or to put it another way, the thiosulfate particles are completely outnumbered by HCl's. They're banging into HCl's all the time. We stick in a few more HCl's, they're just going to be banging into roughly the same number of HCl's. So we'd expect the graph to be straight. Now, strictly speaking, it can't really go back. It can't really go back to the origin like that. And some people drew a graph where they had the straight bit there, but then they had a sort of straight line going up. So it's highly likely that HCl is first order as well. In fact, I'm pretty sure it is. But just for the purposes of the excess bit, in excess, HCl would not affect the rate. So we have a change in concentration having zero effect on the rate. Well, anything to the power 0 is just 1. So if I raise HCl to the power of 0, it basically disappears from the rate equation. In fact, mathematically, those two are identical. HCl to the power 0 and nothing there at all has the same effect on K. So a 0 order reactant, or the reaction is 0 order with respect to a reactant, means that changing its concentration has no effect on rate. Now, in the disappearing cross experiment, we actually do this. You normally use, I think it's 0.15 mole per dm cubed thiosulfate, and we often change the concentration of thiosulfate and then use 1 or even 2 mole per dm cubed HCl, albeit usually a little bit less of it, but it's still in excess. Why is that helpful? Why might chemists want to have the HCl in excess if they're focusing on the thiosulfate? It means what? Sure, yeah, but remember we're studying rate. Go on, Eddie.
Would it be because the sodium thiosulfate is actually the independent variable in this experiment?
Right, and the HCl?
That's
Yeah, that's it, controlled.
yeah,
That's
the
exactly right.
HCl
So if we're setting up an experiment where we want the sodium thiosulfate to be the independent variable, we don't want anything else to affect that experiment. Making the HCl excess, making it 0 order, means that it cannot affect rate. Cannot. Even if we measure it slightly wrongly. So if we measure 10 mils the first time and then next time we mess it up and we only measure 9 mils, it doesn't matter. Because it's a control variable by virtue of being in excess. Okay. There's one more situation. HCl is not a factor in the rate equation. That's what 0 order means. It is possible to have a second order reactant. Now, I'll explain later on how this can arise. It's very rare. Most reactants are first order or 0 order if we make them 0 order, but we can have second order reactants. So let's deal with the rate equation here first. So let's imagine that we've got a reaction where A, B and C react together to make D, and the reaction is first order with respect to A, second order with respect to B, and 0 order with respect to C. Could you write me a rate equation for that reaction, please? So I've used A, B, and C here. I should get rid of that. I'll make them X, Y, and Z, just so we're not confusing ourselves. So second order would be raising the concentration to the power of 2. Could you just write me a rate equation now, thanks? Okay. So, most of you have got there now. So our rate constant K times the concentration of A raised to the power of 1, which kind of means just concentration of A. Concentration of B squared, that will obviously matter, and concentration of C to the 0 actually means it would disappear from the rate equation. If you were asked in an exam, either of those would be correct, either with C to the power 0 or just leaving it out completely. They mean the same thing. All right, well, let's just finish with our second order reactant, whatever it was B, wasn't it? So let's have concentration of B here. We're just changing the concentration of B, and we're measuring the rate. What would that graph look like? Just draw me one more. No, it's not one more graph. There's many more coming. You've used up your quota, Addy. Let's pick on someone else.
So do you have to draw all the quadrants because isn't like X squared got to?
Yeah. You can't have a negative concentration, Matthew. So that means that we're just So you should have a graph that starts at the origin, because when the concentration is 0, the rate will definitely be 0. You can't have an experiment without a reactant. You can't have a reaction without a reactant. But it should be a nice graph of y equals x squared, or in this case, of course, rate equals some constant times b squared. Or rate is proportional to b squared. Okay, we're all good. Right. Where do we go next? Do we go to the rate constant? Yes, we do. All right. We haven't really talked about the rate constant. We've just kind of kept putting k's in things. So let's deal with that now. So a common way of working out the rate constant is we'll measure the rate for the set concentration of reactants. So we have a concentration of this and a concentration of that, and then we measure the rate. And that means that we've got all the information in the rate equation except K. So let's do this. We'll stay with the A, B, and C from the previous example. So rate equals K times concentration of A, concentration of B squared. Let's have a concentration of A of 0.1 and a concentration of B of 0.2. And a rate which is 4.1 times 10 to the minus 4. Notice the units, mole per dm cubed per second. Calculate the rate constant for me now. You're going to do this. And state its units, please. And you do that now. How many sig figs are used in the question, Kobe? So it's 2 then. Okay. So I've rearranged it just to make the maths a bit easier. So rate over AB squared. Then we substitute in the numbers. Don't forget to square B. And we get 0.1025. All the data is to 2 sig figs. So the most appropriate number of sig figs is 2. How did we work out units for KC? What was our method there? We sub them in. So if I substitute in the units there, so rate is on the top, that's mole per dm cubed per second, and then units of concentration, just mole per dm cubed, but it's mole per dm cubed squared for B, so we need to take that into account. Okay, so yeah, so we substitute the units into the equation. We cancel the mole per dm cubed top and bottom. That gives us s to the minus 1 over mole per dm cubed squared, which we need to then expand mole to dm minus 6, but it's 1 over that. So our final units will be mol minus 2, dm6, s minus 1. Doesn't really matter about the order you write them in. So like Kc, the units of K are going to change from equation to equation because the rate equation is going to be slightly different for each equation. So you get used to finding K and also finding the units of K. All right. I just said that. Let's do some examples of that, please. Can you just do those 3? Thank you very much. Okay, so do you know what? I'm going to make this a separate video.